Hello, in this video we are looking at second derivatives. To begin with, we need to understand what is meant by a concave and a convex curve. So concave looks a bit like the intersection symbol from statistics, and convex looks a bit like the union symbol. They don't have to look exactly like that, but the idea of which way up they are is the important bit. And for anybody who doesn't know what a cave looks like, this is a cave and looks like a concave curve. So we're going to start with some definitions. For concave, the function f of x is concave on the interval a to b if and only if the second differential is less than or equal to 0 for every value of x in that interval. So we've just seen that a concave curve looks a bit like a cave. Okay. By saying the second differential is less than or equal to 0, what we're saying is that the gradient is becoming more negative. So if you think about the gradient on the left-hand side of the cave, it's a positive gradient. It becomes 0 at the top and then becomes negative as it goes down the other side. So the gradient is becoming more negative as we go from left to right for a concave function. Whereas for a convex function, it's the other way around. The function f of x is convex on the interval a to b if and only if the second differential is increasing, is greater or equal to 0 for every value of x in that interval. And then finally, a point of inflection occurs when f double dash x is equal to 0 and f double dash x has different signs either side of x. So curves can be described as concave or convex or both for defined intervals. So looking at our top left example, we have a negative quadratic that is concave for all values of x. Okay, and if we differentiate it, we get minus 2x. If we differentiate it again, we get minus 2. That is always negative, doesn't matter what x is. So on that basis, it's concave for all values of x. The one top right doesn't really look like my diagrams, but it is convex. Okay, y equals e to the x. If we differentiate that once or twice, doesn't matter, we're going to get e to the x. E to the x is always a positive function, no matter what the value of x is. So the curve is convex for all real values of x again. Whereas our cubic at the bottom is sometimes concave, sometimes convex. We would describe it as concave up to the point labelled x equals 2 and convex from then onwards. Okay, if we differentiate the expression twice, we get 6x minus 12. So when x is 2, we get the second differential equals 0. So when x is less than 2, we get negative numbers. And when x is bigger than 2, we get positive numbers. So it's concave when x is less than or equal to 2 and convex when x is greater or equal to 2. So again, we've just seen a quadratic, a negative quadratic. So if we ask for the interval for which 25 minus x squared is concave, if we differentiate it twice, we get minus 2. That is always negative. And when we say something is always negative, no matter what x is, it means that the interval is going to be minus infinity to plus infinity. For sin x, it's concave in some regions and convex in other regions, as I'm sure you can appreciate from its oscillating periodically. So if we look at, say, 0 to pi, the values of sin x are positive, as we can see from the graph. But if we differentiate sin x twice, we get negative sin x. So all those positive sin x values will then become negative, which agrees with the definition of concave for a function that its second derivative is less than or equal to 0 for every value of x in that interval. And we can use exactly the same argument to show that a region such as pi to 2 pi is convex. Now for points of inflection, such as 0, 0, first of all, if we differentiate sin x twice, as we said, we get minus sin x, and minus sin 0 is still equal to 0. So that agrees that the second derivative equals 0. In terms of different signs either side of x, it probably helps to appreciate that sin x is an odd function, which means that sine of a is the negative of sine of minus a, or in other words, say sine of 0.1 will be the opposite sign of sine of negative 0.1. So if we think about points either side of 0, such as 0.1 and minus 0.1 for x, they are going to have different signs, whether we're doing sin x or whether we're doing minus sin x. So both those conditions for the point of inflection hold for 0, 0. f of x equals x cubed is concave for the interval from minus infinity to 0. It's convex for the interval from 0 to infinity, and it has a point of inflection at 0, 0. Its second derivative is 6x, so when we substitute a negative number into that, we get a negative answer, which is why it's concave from minus infinity to 0, whereas if we substitute a positive value of x into 6x, we get a positive answer, so it's convex from 0 to infinity. As regards the point of inflection, when we substitute 0 into 6x, we get 0, so it agrees with that first rule for the point of inflection. And if we substitute a negative number or a positive number like negative 0.1 or 0.1 into 6x, we get a negative and a positive answer. So f double dash 0 is 0, and it has different signs on either side of that point. Hence 0, 0 is a point of inflection. F of x equals x to the 4 is convex for the entire interval from minus infinity to infinity, but it does not have a point of inflection at 0, 0. So the second differential of x to the 4 is 12x squared, and because when we square a number it makes it positive, that's why it's got a positive second differential for all values of x from minus infinity to infinity. As regards the non-existent point of inflection, although f double dash 0 does equal 0, we don't get different signs on either side, because if we substitute negative 0.1 or positive 0.1 into 12x squared, for example, we still get the same answer of 0.12. So it's not a point of inflection because f double dash x does not have different signs on either side of x. We are going to finish this video with a worked example. A function is given as f of x equals 10 plus 99x minus 12x squared minus 2x cubed. We've been asked A, to show that f of x is concave in the interval 2 to 4. We've been asked to find the point of inflection of f of x, and then as a result hence state the interval for which f of x is convex. So the first thing we have to do to show that f of x is concave in that interval is to differentiate it twice. F dash of x is 99 minus 24x minus 6x squared, and then f double dash x is minus 24 minus 12x, which is a linear function. Okay, now clearly it's less than or equal to 0 between 2 and 4. If we put 2 into it, we get negative 48. If we put 4 into it, we get negative 72. And because it's linear, we're going to get all those values between minus 48 and minus 72 for x values between 2 and 4. Hence, it is concave in the interval 2 to 4 because f double dash x is less than or equal to 0 in that interval. For part B, we've been asked to find the point of inflection of f of x. So just as a reminder, a point of inflection occurs when f double dash x is equal to 0 and f double dash x has different signs either side of x. Now we've already worked out the second differential as minus 24 take away 12x. So if we put that equal to 0 and solve it, we find that x is negative 2. So there will be a point of inflection at x equals negative 2 if f double dash minus 2 has different signs either side of minus 2. So if we consider, for example, minus 1.9 and minus 2.1, substituting minus 1.9 into f double dash x gives us negative 1.2, whereas sticking minus 2.1 in there gives us positive 1.2. So we have different signs either side of our negative 2 value for x. Hence there is a point of inflection at negative 2. And we can work out what y is by going back to the original function. So 10 plus 99 times negative 2, take away 12 times negative 2 squared, take away 2 times negative 2 cubed, gives us negative 220. So the point of inflection is at negative 2, negative 220. And then we can have a look at the graph and we can tell straight away where it will be convex. So this is the graph of the function we've been looking at in this example. And as we've just determined, there is a point of inflection at negative 2, negative 220, as shown by the arrow. So to the left of that point, the graph will be convex, and to the right, it will be concave. So the interval for which f of x is convex is negative infinity to negative 2. Thank you very much.